Here we are going to discuss how to find the eigenvalues and eigenvectors of a matrix. So let's start with the definition first. So the definition, a number lambda, so lambda is called an eigenvector, is called an eigenvector, eigenvalue, that's one word, eigenvalue of a n of an n by n matrix of an n by n matrix A if there is a non-zero, it's very important, non-zero vector, let's call nu, such that AV equal lambda V. So what happened when if there is a lambda and V such that AV equal lambda V, we call lambda the eigenvalue and V the eigenvector. So such a V is called an eigenvector associated with the eigenvalue lambda, eigenvalue lambda. So this lambda can be real or complex, so it can be a complex number as well. Yeah, so that's the definition. Lambda is called an eigenvalue of an n by n matrix. So we have a n by n matrix. If there is a non-zero, it's very important, non-zero vector such that this condition satisfies, AV equal lambda V. Such a V is called an eigenvector associated with the eigenvalue lambda. So that means if there's a lambda, it's going to give you a vector. It's not like any vector, because you can see that this is like a very rare case. So AV equal lambda V. Lambda is just a number. So what's going to happen? We know that when you multiply a vector with a matrix, what's going to happen is going to kind of distort the vector. So what it says that it simply equals to a scaling of the original vector. So that does really happen, because A can do like a big distortion to the vector, but this says that it is only a scaling of the vector. So that's like a very rare situation. If that happens, we call that lambda is eigenvalue and the V is the corresponding eigenvector. And it is really interesting, if V is eigenvector, K is a number, any scale of that is also eigenvector. So it's like interesting fact. So let's write that just as a note. If V is an eigenvector, any non-zero multiple, any non-zero, doesn't look like non-zero, any non-zero multiple of V is also an eigenvector. And then if you know a little bit more linear algebra, there's another fact. What it says that the eigenvectors form a subspace. Eigenvectors we can say the eigenvectors form an subspace called the eigenspace. The basis vector, because any vector space has a basis. The basis vectors are called the eigenbasis. So there are a few things that's interesting. So there's a kind of thing, but those are like not really necessary. But just to know, like, what's out there. So what it says that eigenvectors form a subspace. Eigenvectors form a subspace called the eigenspace. The basis vectors, because we know that any vector space has a basis. So those basis vectors are actually the vectors called the eigenbasis. Good. So let's see how to find the eigenvectors. So that's the eigenvectors and eigenvalues. So let's talk about those two steps now. Uh, so there are two steps. Now the question is how to find eigenvalues and eigenvectors. So let's talk about that. So there are two steps. The first step, when you want to find the eigenvector, is always first find the eigenvalues. So let's start with that. So the step 1, find eigenvalues. Find eigenvalues. So to find eigenvalues, what we can do, we're going to solve the characteristic equation. So what we do is find the zeros. Find the zeros of the characteristic equation. Find the zeros of the characteristic equation. So characteristic equation. What is that? That is simply the determinant of a minus lambda I equal 0. So that's what we call the characteristic equation. You can see that when you expand it, it's going to be a polynomial in lambda. So and then what we're going to do, we're going to find the zeros of that. Those zeros are the eigenvalues. That's the definition. That's the first step. And then the second step, we find eigenvectors. Find eigenvectors. So when you find eigenvectors, which are 6 steps, so we can use what we call the Gauss-Jordan elimination process. So what we try to do is eigenvectors means the basis for the null space. That's another way. So what, in other words, this is the basis for the null space of A minus lambda I. For each eigenvalue, we try to find the basis for the null space. The basis for the null space are the eigenvectors, those basis elements. Okay, so we're going to find the basis for the null space. So let's do that. So which needs 6 steps. So the first step, we're going to simplify. For each eigenvalue, we simplify A minus lambda I. Let's say lambda I, okay, that's the one eigenvalue. Simplify A minus lambda, that's the first step. The second step we're going to do is find the reduced echelon form. Find the reduced. I'm going to put this in parentheses. It's not really necessary. I'm going to explain why we don't really need that. So find the reduced echelon form of a minus lambda I slash 0. So that's the augmented matrix. So we find the reduced echelon form of the augmented matrix. Step number 3. There are 6 steps. Write the corresponding system. After we do that, then we can write the corresponding system. So write the corresponding system. Write the corresponding system. And then the fourth step, we're going to do solve for the basic variables in terms of the free variables. Solve for basic variables in terms of free variables. It's very important. We solve for basic variables in terms of free variables. It will be very clear what we mean by basic and free if you don't know that. And then the fifth step, write the parametric vector form. Write the parametric vector form So we get the we simplify, find the echelon form, and write the corresponding system, and go for basic variables instead of free variables, and write the parametric vector form. Once you write the parametric vector form, those vectors are the eigenvectors. And then so basis vectors, the basis vectors are the eigenvectors. So that's the idea. So basis vectors are the eigenvectors. So those are the 6 steps. So let's do a problem, a 2x2 problem, and see how it works. So let's do this example. Find the eigenvalues and eigenvectors of, say, A equal, let's say 3, 1, negative 4, negative 2. So the first step is to find the eigenvalues. So find eigenvalues. So do that. What we're going to do, we're going to look at the determinant of A minus lambda I. So so it's a determinant of A, which is 3, 1, negative 4, negative 2, minus lambda times I. I means the corresponding identity matrix. Since this is a 2x2 matrix, we can write the 2x2 identity here. So if it's a 3x3, you have the 3x3, like that. Okay, so let's simplify this inside. So it's a determinant of, so you're going to subtract, so we can write this one as 3, 1, negative 4, negative 2. We can multiply by lambda. That means you're going to multiply all the entries. So that means it is lambda 0, 0, lambda. Now we can subtract the corresponding entries. So that means it is a determinant. We subtract the corresponding entries. Since the off diagonal entries are 0, you only subtract from the diagonal entries. That is 3 minus lambda and then negative 4, and then we have 1 here. This is negative 2 minus lambda. So that's what you get. Now we can use the determinant notation. So we can say this is simply determinant of 3 minus lambda, 1, negative 4, negative 2 minus lambda. And this is a 2 by 2 matrix, and we know that when you have the 2 by 2 matrix, what is the determinant? So I'm going to recall that. So when you have a 2 by 2 A, B, C, D, the determinant is simply A, D minus B, C. So we can use that fact here. We're going to multiply the main diagonal first, and then subtract the off diagonal, the other diagonal, opposite diagonal. So if you do that, and then what we're going to do, we're going to set this determinant equal to 0. So let's do that. So that means first you're going to multiply them. So we can have 3 minus lambda, negative 2 minus lambda, and then we have negative 4 times 1 means negative 4, but you subtract, that means positive 4. What we can do, we're going to set this equal to 0, and then we can look at the factors. So first we can expand this. So you're gonna, what are you gonna get? You're gonna get lambda squared, and then we have negative 3 lambda, positive lambda, so you get negative lambda, and then we have negative 6, and then we have a plus 4, that means negative 2 equals 0. That's what you get. And you can see that this one has nice factors. Those are lambda minus 2 and lambda plus 1, so it equals 0. So this says that lambda equal negative 1 and 2, and these are the eigenvalues. So those solutions are the eigenvalues. Okay, so it is negative 1 and 2. So let's write that. So the eigenvalues are lambda equal negative 1 and lambda equal 2. Now what we're going to do, for each eigenvalue, we're going to find the corresponding eigenvector. So let's do the second step. So step number 2, find eigenvectors. Find eigenvectors. That means what? The basis elements of the null space. So find, in other words, find basis elements. Find basis elements. Find basis elements of the null space. Of the null space A minus lambda I. That's what I'm trying to do. So it's just a null space situation. We know how to find a null space. That's a simple idea. We're going to put A minus lambda I augmented with 0 and row reduce, find the solution. It's just find the solution of the system. Okay, so we can write that. So that is, find the solutions, find the solution of A minus lambda I x equals 0. So we just try to find these solutions. Those are the null space. Okay, so we're going to go one by one. So for lambda equal negative 1, so we can write A minus lambda is negative 1 I, which is 3, 1, negative 4, negative 2, negative negative become positive, I means 1, 0, 0, 1. So we're going to add them. Once you add them, what's going to happen? You're going to add the corresponding entries. So it becomes 4, 1, and then negative 4, and then negative 1. Now what we can do, we can look at the so that we simplify that, and then we do the augmented matrix. So we can go with A minus lambda I 0. You look at that we already know because we already simplified that side. So it become 4, 1, negative 4, negative 1 augmented with 0, 0, and we can do the row reduction. What we can do is we can simply add the first row to the bottom row. So let's do that. So once you do that, you do R1 plus R2. So that if you do that, you're going to get 4, 1, 0, 0, 0, 0. That's what you get. And you can see that once you get a 0 row like that, and then you can see, so this is the reduced form. The question is, do we really need the reduced echelon form? We do not need the reduced echelon form. This is perfectly fine, and also you get good results for that. So now what we can do, we can write the corresponding system. So write the corresponding system. So write the system. So write the system. So what's the system for this line? If you look at the first line, you can see that the system is 4x1 plus x2 equals 0. That's one. And then you can see that that's the only equation we're going to get. And then you can see that x2 is a free variable. So you can pick anything you like as a free variable. You can pick either x1 is a free variable, x2 is a free variable. It doesn't really matter. What we normally do is, since you have x2 already like that, what I'm going to do is we're going to take x1 as a free variable. So you can see that that's a little bit away from the standard argument, because just to avoid fractions we do that. Because you can see that there's a 4 here. So if you pick x1 as a free variable, x2 is simply becomes negative 4x1. So it's much easier. So you write the corresponding system. Now the next one is, and then you can see that also x2 is x1 or x2. So it doesn't matter. Is free. One of them is free. So I'm going to say x1 is free, and x1 is free. We do that intentionally. Now the next step is write one variable. We can say basic variable, it doesn't really matter, as the in terms of free variables. Okay, so write a basic variable. So in this case, I'm going to parenthesis basic variable, because I'm going to go a little bit away from that, even though we say that. So write basic variables in terms of free. In terms of free variables. So in this case, what we can do is, I'm going to solve for x2 actually. So x2, that's actually the free variable in the regular terms, but we're going to go, so it's a negative for x1, and x1 is free. So we did that. So you solve for basic variables. It's not really the basic variable in this case. You solve for one, the easy one, from the hard ones. Okay, good. Now what we can do, we can write the matrix. Okay, so write the parametric vector form. So write the next step. Write parametric vector form. For that, let's assume the vector v, which has two components, x1 and x2. Those are two components that we found. So we're going to substitute. X1 will leave, but x2 is negative for x1. Now you can see the benefit. You can pull the x1 out. So it's simply 1 negative 4. There are no fractions. But if you do the other way, if you try to find the reduced echelon form, there are fractions here, or this no fraction. And then what we can do, we're going to call x1 is a t, it's a parameter, and 1 negative 4. So t is any, we can write it there. So t is any real number. T is any real number called a parameter. As a parameter. Okay. So that means the eigenvector is 1 negative 4. So the eigenvector is v1, we can call v1, which is 1 negative 4. Good. So that's for the first eigenvalue. So we do the same thing with the second eigenvalue as well. So let's do that. Now for lambda equal 2, we do a minus 2i first. We're going to simplify that. So it is 3, 1, negative 4, negative 2, minus 2 times 1, 0, 0, 1. So we can subtract. So we're going to get 3, 1, negative 4, negative 2, minus 2, 0, 0, 2. So if you subtract, you're going to get 1, 1, negative 4, negative 4. Now we can write the augmented matrix A minus 2i augmented with 0. So let's do that. So you're going to get 1, 1, negative 4, negative 4, 0, 0. And this is very simple. So what we're going to do, we're going to multiply the first one by 4 and add it to this bottom one. Then you're going to get 1, 1, 0, 0, 0, 0. Good, that's the echelon form. Write the system. Write the system. System is x1 plus x2 equals 0, which says that x2 equal negative x1, and then x1 is free. So you can see that we kind of slightly go away from the standard echelon argument. We normally pick x2 as the free one, but we're going to pick x1 as the free one. Yeah. So x1 is free a variable. So we normally pick x1 as like parameter t or something. Good, and then write the parametric vector form. So we can write the parametric vector form. So x, so we can call v the vector which has x1, x2 components. Now we can substitute. We can substitute x1 as x1, x2 is negative x1. That's what we got, and then we're going to pull the x1 out. So 1, negative 1, and then we can say x1 is a real number. Okay, that's a parameter. And this is the vector we are looking for. Actually, it's a v2 now. So that's the v2 we are looking for. So the eigenvector v2 equal 1, 1, or any multiple of that. Okay, so that's it. So it's a very simple argument.